Hi, y'all.
Hello.
It is 8 o'clock, so let's start. Um, let's start off with anybody who's got specific questions about, should we start on the multiple choice practice probably? Let's start there. So if you've got a specific question, just unmute yourself, holler it out, and we'll work it out.
I think if I had a question, it would be over um like when to use specific formulas for pressure, like with ideal gases, if that makes sense. So like when to use like the P1V1 equals P2V2 versus like the other one about like or then when to do like the Dalton's law equation.
That is probably a really good question. It's not probably a good question. It's a fantastic question. It's a lot of looking at the problem to really see what's going on in the problem. So we've got, let me pull something else up. Let's do it this way. So like you said, we've got a whole bunch of different situations where they're going to be talking about pressure in some way, shape, or form. And so we've got the combined gas law. So we're going to use this particular equation when the problem says something about that our situation is changing somehow. So like it says, hey, we started at this volume and we've increased the volume to this. How did that affect the pressure? Or we say we changed our pressure from 1 atmosphere to 2 atmospheres. How did that affect the volume? So this is all about changes. And then we've got good old Puvnert. So Puvnert is more about a single situation. So this is about a single gas hanging out. We know some information about it, but there's some fact that we don't know about it. So like saying, hey, you have this gas sitting in a 5-liter container at 25 degrees Celsius. What's its pressure? So it's a single gas. Nothing is changing. Okay. And then what else have we got? Then we've got the stuff about Dalton's law of partial pressures. So we've got the one about the mole fractions. So we take the mole fraction of that particular gas multiplied by the total pressure to give us the pressure that that gas provides to the situation. So this would be if we know that we have a mixture of gases all in the same container.
Can you please explain that again?
So we would use this equation if we have something that is a mixture of gases all in the same container. Let me see. I know there was a question like this on your Friday quiz last week, right? The one about if we put here. So on the multiple choice, this question number 45, can you see this? This guy. So it says a gas mixture at 0 degrees Celsius and 1 atmosphere contains 0.01 moles of hydrogen, 0.015 moles of oxygen, and 0.025 moles of nitrogen. So if the whole container has a pressure of 1 atmosphere, we want to know the partial pressure of hydrogen gas. So hydrogen is only 0.010 moles out of the total mixture of gases, which is 0.010, 0.015, and 0.025 moles altogether. So if we add that together, 25, 35, 40, we get 0.050 moles. So that's my mole ratio, because I've got that many moles of hydrogen in that many moles of gas total. And then I multiply that by my total pressure in the whole container. Because whatever fraction of the mixture hydrogen is, it's going to provide that same fraction of the pressure to that mixture. So this would give us the pressure of just the hydrogen gas. If instead we knew their pressures, then we could just, Dalton's law says that any gases that get mixed together, as long as they're in the same volume, their pressures are just going to add together. And then the only other thing about pressures was like what we did with the lighter lab, where we have to subtract away the vapor pressure of water. That's going to be really obvious in the question. I know there's one on your free response like this. Because it's going to come straight out and say, hey, the vapor pressure of water at this temperature is this. And so you're going to know what that number is to be able to subtract it away from your total pressure. Now that I need this, I'm not going to be able to find it, am I? Here it is. So on free response question number 11, says, as the magnesium reacts, the hydrogen gas produced is collected by water. So that's sort of a big hint. Water displacement at 23 degrees Celsius. The pressure of the gas in the collection tube is measured to be 749 torr. And then it says, given that the vapor pressure of water is 21 torr at that temperature, calculate the pressure that the hydrogen gas produced in the reaction if it were dry. So dry means without that water vapor there. So we take that pressure that we measured in the container, subtract away the vapor pressure of water, and that leaves us with the pressure of just that hydrogen gas. Because that 749 torr is the pressure of our hydrogen gas plus the vapor pressure of water. So that's sort of the last thing that we've got that deals with pressure. That was a lot of stuff, but we hit a bunch of it. Any other questions or any questions to let's first off, does anybody have any questions you want to continue on about any of these pressure things? Any clarifications that you need? By your silence, I'm going to assume we can move on. So let's go back and let's say, anybody have any specific questions about any of the multiple choice?
I didn't understand number 59.
59. Okay. The experimental apparatus represented above. So we talked about that when we talk about when gases diffuse, we're just talking about those gases moving. So we're going to be talking about speed and stuff like that. When the cotton balls are placed at the end of the tube at the same time, the gases diffuse from each end and meet somewhere in between where they react to form a white solid. Which of the following combinations will produce a solid closest to the center of the tube? Ooh, this is deep. All right. So if we want this to be closest to the center of the tube, this gas is going to move this way, this gas is going to move this way. If we want it to meet in the center, we want both of those gases to have about the same speed so that they'll meet in the middle at the same time. And so in order for those gases to have the same speed, they would need to be at the same temperature, which we're going to assume that they are because they're sitting in the same tube together. And they didn't say anything about them having different temperatures, but we also want them to have close to the same molar mass. Remember that molar mass also controls how fast gases move. And so we want whichever combination gives us the closest, those two substances to have the same molar mass as each other. So I can tell right off the bat that it's not going to be HBr and NH3 because Br's got a pretty high mass. 12, 13, 14, 15, 16, 17, plus nitrogen is 14. So that's 31. What's the molar mass of bromine? Oh my gosh, I don't have a periodic table on my desk. What am I doing? So bromine's mass is 79. That's almost 80. That's big. So my guess is that A is the answer, right? Because HCl would be around 36 and CH3 and H2 would be around 31. That's the closest molar masses we can get out of any of those combinations.
Okay, yeah, that makes more sense now.
Okay. Any other multiple choice questions you'd like to go over?
Can you explain 56?
Sure. $56. Ooh, okay. So normally a question like this would give a little bit more information. They would say something about that they were all in the same container or that you had the same number of moles of each one of these. And so there'd probably be some extra information in a question like this. The density of the gas is in grams per liter. So it means we need the most mass in the amount of space that we've got available to us. If we look at all of these gases, they're all at the same temperature, so that's not going to influence anything. They don't tell us anything about volume, so let's pretend that they're all at the same volume. But we can see that gas B has got twice the pressure. So in order to be able to get a lot more pressure out of there, there's got to be a lot more particles in that gas to be able to provide that pressure. So since The molar mass comparison is not quite, it's a little bit more than half of the mass of this, and we've doubled the volume or the pressure also. That means that there'd be more particles in here than there would be in the butane. So more particles, same volume, means that the density would be greatest in B. Now, if all of these pressures had been the same, if they all had been 2 atmospheres, then the thing with the greatest density would have been butane, because it provides the most mass per particle. And if they would all have the same number of particles, then it would have the greatest density. Any other multiple choice questions you'd like to go over?
Wait, so the density is based off of the pressure, and then the kinetic energy is based off the temperature?
So the density is related to pressure in this case because the pressure is telling us which one of these gases has the most particles in it at this time. So since the temperature is the same for all of them, since they didn't tell us anything, we're going to assume that the volume is the same for all of these containers. So the only thing that could provide more pressure would be by putting more gas in that container.
Okay. And then, but is the average kinetic energy, is that just based off of temperature?
Correct.
Okay.
So why don't we use this as an example real quick then to talk about kinetic energy since you're asking about it. So if we were using these same 3 gases, they all are at the same temperature. So if all of these gases have the same temperature, that means they're all going to have, that's an arrow, I promise it's an arrow. It means they're all going to have the same kinetic energy. So the only thing that controls kinetic energy is temperature. But what about speed? Now, when we say speed and velocity, we use those sort of interchangeably. They mean the same thing. So which one of these is going to move the fastest? So we got to think, is one going to be faster than the others, or because they all have the same kinetic energy, or are they all going to move at the same speed?
Does the molar mass have any effect on the speed or no?
Yes.
Okay.
So the speed is controlled both by temperature and molar mass.
Okay. And then the kinetic energy is only based on temperature?
Correct.
Okay.
So since all of these are at the same temperature, they all have the same kinetic energy. But because methane has a much smaller molar mass, it is going to be the fastest of these gases. Of these 3 gases, it means the slowest one, the one with the least amount of velocity, would be the butane, because it has the highest molar mass.
Could you explain number 80, please?
Number 80. Ooh, okay, big fancy words. An equimolar mixture of N2 and argon. So equimolar means we've got the same number of moles of each, is kept inside a rigid container. So that means my volume is going to be constant at a constant temperature of 300 Kelvin. So volume and temperature not changing. The initial partial pressure of argon in the mixture is 0.75 atmospheres. An additional amount of argon was added to the container enough to double the number of moles of argon gas in the mixture. Oh my God, there's so much changing. Assuming ideal behavior, what is the final pressure of the gas mixture after the addition of the argon gas? Whew. Okay. So, if initially argon was providing 0.75 atmospheres of pressure, that is related to argon's mole ratio. So they told us that we had an equimolar mixture of nitrogen and argon, which means, to be totally honest, let's pretend like this is easy. Let's pretend like we've got 1 mole of each. If I've got 1 mole of each, that means argon is 1/2 of the mixture, right? Even if we had 10 moles of one and 10 moles of the other, argon would still be half of the mixture. So Dalton's law of partial pressures tells us if we want to know the pressure of argon, we take the ratio, the mole ratio of argon in my mixture, and multiply it by my total pressure. I don't know my total pressure, but I know my mole ratio because I know that argon is half of that mixture initially, and I know the pressure that it gave me. So if my pressure of argon is 0.75 atmospheres and argon is half of the mixture, that means that initially my total pressure was twice the pressure of argon. So twice 75 would be the 1.5, right? So that was my total pressure to begin with. If I add in more argon, enough to double the number of moles of argon gas in the mixture, what is that going to change my mole ratio of argon to? It was half of the mixture. But if I double this, if it's 2 moles out of 3, or if they each were 10 moles, it'd be 20 moles out of 30 moles now. So argon is moving up to be 2/3 of the mixture. So if argon is 2/3 of the mixture, it's also going to be providing 2/3 of the pressure. And if that number of moles provided this much pressure, it's going to increase the total pressure in the container. But it is not going to change the pressure of the nitrogen. That nitrogen is still hanging out in there. It's still the same container. It's still the same nitrogen. So the pressure or the partial pressure of nitrogen is not going to change. So the final pressure of the mixture after we add the argon, it can't be less than what we started with, or the same as what we started with. We added more gas, which means we need to increase the pressure. I'm gonna cheat because I don't feel like doing math right now. What's the answer? Okay. La, 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 la. So if I doubled the amount of argon, it's like I'm adding in, it's sort of like I'm adding in a third gas, right? So my argon initially provided 0.75 moles of pressure. So how can I write this out? Let's go. Initially, argon provided 0.75 atmospheres of the pressure, which means that my nitrogen also provided 0.75 atmospheres of pressure. Let's say I add in a third gas. That's the same number of moles. It's also going to provide the same percentage of pressure, right? So my argon that I'm adding in new is also going to provide 0.75 atmospheres of pressure. This mixture, it doesn't care whether that's more argon, it doesn't care if that's nitrogen, it doesn't care if that's hydrogen gas. There is no property of that gas involved in here. It's just, hey, how many moles of gas do you have? We're at a constant volume, we're at a constant pressure or constant temperature. The only thing that's going to be able to change is pressure. We don't care what gas you are. So by doubling the moles of argon, we're also going to double its pressure. So we get D. That's a lot. That's a big question. All of these are big questions.
Can you go over number 77?
77. All right, we got ethane, we got butane, we got molar masses. The molecular formula molar mass, based on the information, which compound has a higher boiling point, and why is that compound's boiling point higher? Ooh. Okay, so if we're talking about boiling points, they're giving us formulas. This is probably an intermolecular force question. So if this is an intermolecular force question, we got to think about the structure of these two molecules. They tell us that they are straight chain hydrocarbons, which that might not mean a whole lot to you, but straight chain hopefully sort of triggers and goes, they must be in a straight line. So ethane is 2 carbons with hydrogens, 4, 5, 6. Butane is 4 carbons in a straight line with those 10 hydrogens around it. So thinking, structure-wise, these are both nonpolar molecules. They're very symmetrical. They're carbon-hydrogen bonds. So the only thing that we can compare is their London dispersion forces. So we got to talk about polarizability. I know, it's your favorite. So the ethane with those 2 carbon chains has got a certain surface area of that molecule. Butane with the 4 carbon chain, that is going to be a larger molecule. It's going to have more surface area. Since they're all made of the same bonds, we can't really talk about differences in sizes of the atoms or how many electrons they got or any of that mess. So we're really talking about surface area here, how big that molecule is. So the butane has got more surface area. It's going to be easier with that more surface area to interact with other molecules. So I want C4H10 to be the answer. So C and D are out. A says more hydrogen atoms resulting in more hydrogen bonding. Nope, hydrogen bonding only happens when hydrogen is connected onto a nitrogen, an oxygen, or a fluorine, not a carbon. So B makes sense since it's got more electrons, aka it's bigger, it's more polarizable, and it's going to have stronger London dispersion forces. Lots of times they just say dispersion forces. We call them London dispersion forces.
Okay, so when you say electron, you say surface area, and then in the big ideas thing,
Yeah.
it said that we needed to know electron placement. Is that the same thing?
Both of 2 things sort of get wrapped up in electron placement. One of them is how many electrons there are. And then the other one is about like thinking about lone pairs of electrons. when we're talking about polar things. So yeah, when we're talking about non-polar things, we're talking about where those electrons are, how many electrons are in that molecule, how polarizable is it.
Makes sense.
I'm glad. Next.
I don't really get the importance of deviations.
Okay. So I'm gonna write this out separate because there's a lot of it. So when we do all of our normal math, normal calculations, normal figuring out for anything for a gas, we assume that that gas is what we call ideal. So to be an ideal gas, we need to have no intermolecular forces going on. And we need to, we sort of make an assumption that the particles are tiny enough that the size of the particle doesn't affect the volume of the gas. So like when we say we have a gas in a 1 liter container, we're assuming that the particles themselves aren't really taking up any of the liter, that they're just bouncing around inside that liter container. So anything that messes with those two assumptions that we make is what we call a deviation from ideal, or make something act not ideally. So if we want something that's not ideal, a couple different things can happen. If we want to, maybe not want, if we end up maybe having some intermolecular forces happening in there, that's going to affect a couple different things. So if I have intermolecular forces present in a gas, that's going to cause those gas particles to stick together a little bit. Now, they're not going to be super strong intermolecular forces. There's not going to be a ton going on, but they're going to stick and it's going to slow them down a little bit. So it's going to do one of two things. It's possibly going to decrease the pressure, because it's going to, if those particles are sticking to each other, that's less collisions they're going to have with the container. The other thing that having intermolecular forces can do is that it can decrease the volume. Because again, if those particles are sticking together, they're not taking up as much space, they're not bouncing all over the place as much, so it's going to decrease the volume a little bit, depending on what's being held constant and what's not. If we have to take into account the particle volume, then that is really only going to affect the volume. So if we take into account the particle volume, it is going to increase the volume of our gas above what we would expect it to be. So we have some things that we can, some variables we can change or control to make things either behave more or less ideally. So if we want an ideal gas, in order to decrease those intermolecular forces, we want to have a very high temperature, because that's going to make those particles move around faster, giving them less time to bump into each other. And we also want to have lower pressures, because lower pressure means we're not squeezing those particles so close to each other, so they're not going to interact as much. when we want to not have to worry about having to take into account the size of those particles, we want to have smaller gas particles. So we want to have things like hydrogen or helium that are smaller. Number one, that's going to have them be less likely to have intermolecular forces in the first place, and it's also going to mean that they're taking up less volume in that container. So then the opposite of all of those is true if we have a deviation from ideal. So not ideal gases would happen at lower temperatures, at higher pressures, and those are going to be our larger molecules. So I know there's a bunch of multiple choice questions that sort of talk about all of those things involved. And it's just a matter of what they're asking you about as to whether you're talking about intermolecular forces or whether you're talking about the volume of the particles themselves. Did that help?
Yeah.
Okay.
Can you explain 42?
Yes. That is not what I want. I want this. $42, you said?
Yeah.
Oops, too far. All right, so this goes along with what we were just talking about the ideal gases. So which of the following best helps explain why the pressure of a sample of methane, which has a molar mass of 16 grams per mole, is closer to the pressure predicted by the ideal gas law than a sample of ammonia, which has a molar mass of 17 grams per mole. So what they're saying is that methane is closer to the pressure predicted. So they're saying that methane is more ideal and that NH3 is less ideal. So even before I take a look at my choices, I'm going to look at these two gases and I'm going to say, well, their molar masses are really close to each other. So the size of the particle probably isn't going to make a huge difference. CH4, ooh, that's going to be a nonpolar molecule. NH3, that's going to be a polar molecule because NH3 has got that lone pair of electrons on top. So maybe it's going to be an intermolecular force thing. Let's see what the choices are. So it says for A, NH3 molecules are polar while CH4 molecules are not. Ooh, okay, that's true. And the greater attractions between the NH3 molecules cause the molecules to collide with the walls of the container with less force. Let's hold on to that one. That might be a possibility. NH3 molecules have a greater molar mass than CH4, so they collide with the walls with more force. They're really close to each other. That 1 gram per mole is really not going to make that much of a difference. So I'm going to say B is out. CH4 molecules have more hydrogen atoms than NH3 molecules. So CH4 molecules have more hydrogen bonding and greater intermolecular forces. Heck no, CH4 does not have hydrogen bonding. And then D says CH4 molecules are larger than NH3 molecules, so the actual CH4 molecule take up a significant portion of the volume of gas. Even if CH4 was larger than ammonia, they told us that CH4 acts more ideally, and that means that we would want it to have smaller volume because it wouldn't be taking up volume. So that one is out. So I'm going to go with A.
How does it being polar cause it to have a greater attraction though?
Because if it's polar, it has, in this case, it's going to have hydrogen bonding for an intermolecular force. So if it bumps into another NH3 molecule, it's going to be more likely for those two molecules to stick together and have an intermolecular force between them, even if it's short, than two CH4 molecules will.
Can you go over 40?
40. Ooh, big pictures. Okay. Sodium chloride and magnesium sulfide are represented, which statement correctly identifies diagram 1 and identifies the compound with the lower melting point, explaining why. Ooh, okay. So both of them are ionic compounds. So I know that they're both being held together because of charges. That's how ionic bonds stick together. So sodium chloride is made of sodium plus and chlorine minus. Magnesium sulfide is made out of Mg2 plus and S2 minus. So I've got a difference in charge here. I've also got a difference in size, but not a drastic difference in size. So let's see. The difference in my pictures, it really looks like the only difference is in the size of those atoms. Everything else looks pretty much the same, doesn't it? So it says diagram 1 represents sodium chloride. It would have a lower melting point. Well, let's figure out melting point first, because that might help us narrow this down. So melting point is controlled by strength of the forces holding everything together. So in this case, it's the force of the ionic forces holding everything together. Sodium is held to chlorine, plus and minus are attracted to each other. Magnesium and sulfur are attracted with a +2 -2. Since I still got my periodic table up here, so magnesium is going to be a little bit smaller than sodium. Chlorine is going to be smaller than sulfur, right? Because it's right there, yeah. So size isn't a huge difference. This charge thing is going to be a big difference. So magnesium and sulfur are going to be held together with a stronger force because of that +2 -2 instead of the +1 -1. That goes back to those Coulombic forces that we've been talking about forever. So MgS is going to have the higher melting point. So can we kick anything out? So MgS has a lower melting point than NaCl. That is not true. MgS has a lower melting point than NaCl. That one is out. So we're stuck with diagram 1 representing NaCl. So that's not going to help us narrow it down between A and B, but let's see if the explanations are different. So this one says sodium chloride has a lower melting point than magnesium sulfide because the Coulombic attractions between the singly charged sodium and chlorine ions are stronger than those between the ions in MgS. That's backwards. The singly charged ones are going to be more weakly attracted to each other. So let's check and make sure B says the right thing. The Coulombic attractions between singly charged sodium and chlorine ions are weaker than those between the ions in MgS. That is true. Any other questions for the multiple choice or anything in general, honestly?
Can you explain Coulombic attraction?
I know this always bugs you, Jack. So remember, we've been talking about this for forever. So Coulombic attractions are based on two things. They're based on charge, and they're based on the size of the particles that are being attracted. So we've talked about this between protons and electrons. We've talked about this between positive and negative ions. So the larger the charge, the stronger those things are going to be attracted to each other. So like the difference between a +2 and -2 ion versus a +1 and -1, since the +2 -2 has a larger charge, those are going to be a stronger attraction to each other. We talked about the same thing. The more protons you have in the nucleus, the stronger those electrons are going to be attracted to the nucleus. And then we also can talk about the size of the particles that are being attracted. So let's say we were talking about, let me pull my periodic table back up. Let's say we were talking about lithium chloride and sodium chloride. So if we were talking about lithium chloride and sodium chloride, they both have the same charge, so that's not really going to affect the attraction between those two. But since lithium is smaller than chlorine, or sorry, lithium is smaller than sodium, that lithium and chlorine are going to be able to get closer to each other than the sodium and the chlorine will, right? That distance between the center of this atom and the center of this atom is smaller here. So that's going to be a stronger attraction because those particles are smaller. So those two factors can affect things. Now this isn't going to work for talking about London dispersion forces. This is not going to work for dipole things. This is only working for things that are charged, like full on absolutely charged. So protons and electrons have full on plus and minus charges. Ions have full on plus and minus charges. So don't start trying to make Coulomb's law work for things that have London dispersion forces. It does not fit there. Next question.
Okay, so I feel like I should understand this one, but I don't know if it's just like the answers that are kind of messing me up, or it's number 46.
Okay. This one has got a little bit of a tricky to it. So this is a Dalton's law of partial pressures question. We've got two gases that start off, I don't know why my picture is so fuzzy, that start off separated from each other. It says that the temperature is held constant. It says we have equimolar samples, so we've got the same number of moles, and that each gas occupies the same volume. So if we've got constant temperature, we've got the same number of moles, we've got the same volume, it means that those two gases should have the same pressure. So I'm going to call that pressure, big P. Okay, so they should be equal to each other. When we remove this barrier in the middle, we allow those gases to mix together, but there's something else that changes when we remove that barrier. We're also changing the volume of the container now. So at first, the left side gas was only in half of that whole big container. So let's say that that was its volume. When we move over here, now it's twice the volume. So when we change the volume, we are going to change the pressure of that gas. So now that, I'm going to call it gas 1, just whichever one is on the left. So gas 1, it's the same number of particles, it's the same temperature, but it's got twice the volume to be able to bounce around in. Pressure and volume are inversely proportional. So if it's twice the volume, that means it's got half of the pressure now. Same thing for gas 2, this one on the right. That was also in a container of size volume. When we remove that barrier, that gas is now able to bounce around that entire twice as big container. So its pressure is also going to get cut in half. Because they're now mixed together, we can add those pressures together to get the total pressure in the container. Total. Okay. So the partial pressure, or the pressure of each one of those gases, is going to be half of its initial pressure. So A and B are out. We did not double the pressure of each individual gas. When we add those two pressures together, it's half of pressure 1 and half of pressure 2. It means that the final total pressure is half of what it would have been when we added them together initially. Because initially it would have been whole pressure plus whole pressure. That would have equaled twice the pressure. So there is this super sneaky thing about the fact that we are changing the volume of that container. College Board likes to throw that in there. There's a free response question that's very similar to this. Where is it? I thought it was a free response question. Nope, maybe not. Maybe it's another multiple choice question. Where it's got containers, like these round, bubbly containers that we open up and the gases can mix together. So as soon as you think about two containers that are connected to each other, maybe I don't have it here. Give me some space. Anytime you've got, like if I've got a big container here that's connected with a valve to another big container. Let's say the volume of this is 1 liter and the volume of this is 2 liters. Right? If I open this valve between these two containers, or I take something out so that those two containers are now open to each other, I now have a new volume. My new volume is now going to be 3 liters. And because that volume has changed, pressures are going to change as well.
Okay, yeah, that one makes a lot more sense now.
And that's something sort of sneaky to watch for.
Yeah.
Other questions?
I think I'm good.
All right. Anybody else? Going once?
Could you go over problem number 44, please, in the multiple choice?
Yes. I knew there was going to be one out there. 44. All right. So this one is, the way this is set up is a little similar to some of the other questions we've seen. They're giving us a little bit more information here. So it says we've got 4 gases. They're all at 273 Kelvin, so they all have the same temperature. The samples are in 4 identical rigid containers, which means they all have the same volume, and that volume is not going to change. If I look at these containers, they all have about the same pressure. But we're looking to figure out what gas this could be. So if they all have the same temperature, the same volume, and pretty dang close to the same pressure. There's another question somewhere in here that talks about how why this is 1.96 instead of 2 is because it's deviating from the ideal gas law. It's such a big molecule that it's affecting its that there's some intermolecular forces going on affecting the pressure. But then it also has a mass of a sample column. So if they're all at the same temperature, the same volume, practically the same pressure, that means they all should also have the same number of moles of gas, right? If we look at Puvnert, if this isn't different, if this isn't different, if this isn't different, then moles can't be different either. So how many moles is 64 grams of SO2? Sulfur has a mass of 32. Each oxygen is 16, so that's 32. Ooh, hey, look, that's 64 grams per mole. And it's got about a mass of 64. So that means that we've got about 1 mole of gas in here, which means that I also should have 1 mole of gas in container 3. So which one of these choices is going to get me closest to 16 grams for 1 mole? Should be A. CH4. Carbon's 12, each hydrogen is 1. So that adds up to a total of 16.
Okay, I reasoned that methane was correct because it was also the smallest molecule of the 4 answers possible. Is that, I don't know, is that a difference?
That might have just been a lucky guess, dude.
Okay,
Because we have this data about its mass, we should base it on that.
so we should go through at least some analysis with ideal gas law and all that.
Just because knowing that everything else has to be the same, it means that we know there have to be the same number of moles in each one of those containers also.
Thank you.
Welcome. All right, y'all. I think I got time for one more question. Who wants to claim it?
Can you do 32?
Sure. All right, 32. Equal numbers of helium, argon, and neon are placed in a glass vessel at room temperature. If the vessel has a pinhole-sized leak, which of the following will be true regarding the relative values of the partial pressures after some of the gas mixture has effused? So again, don't panic about that word effused. It just means leaked out. So if I've got helium, argon, and neon, and we're talking about them being able to leak out of a very small hole in a vessel, then we're going to be needing to talk about the size of the particles, about the speed of the particles. So of these 3, helium is the smallest of these 3. Neon would be in the middle, argon is the biggest. If they're all at room temperature, that means they all have the same kinetic energy, which means that that smallest particle is going to be, number 1, moving the fastest. So it's going to be more likely to be bouncing around and finding that hole. And number 2, also if it's that small, it's going to be able to fit through that hole very easily. So after some time has gone on, a lot of the helium is going to have leaked out of this container. Maybe some of the neon, but probably barely any or much less of that argon has been able to leak out. So after some time has passed, the majority of what's left in that container is going to be argon, which means it's going to be providing most of the partial pressure of that container. So the pressure of argon is going to be the biggest after all that time has passed. The pressure of helium should be the smallest once all that time has passed, because most of it will have leaked out, or at least some of it will have leaked out. So the answer should be A. At the very beginning, because we had equal moles, we would have had equal partial pressures. All right, y'all. It's 9 o'clock. I got to get going. If you've got any other questions, I'll be around tomorrow morning before school. And then we'll do the multiple choice test in class. All right. Thank you all for coming.
Thank you.
You are welcome. And I'll see
Thank you,
everybody
Mrs.
tomorrow.
Blasky.
Thank you.
Bye.
Thank you.
You're welcome.